The absolute value function is a piecewise defined function where the absolute value of x is equal to x if x is greater than 0 and minus x if x is less than 0. We'll be exploring this more when we talk about functions. But for now, we're going to be looking at it in terms of inequalities. Before we do, we have to talk about a few properties. First property is the absolute value of x is greater than or equal to 0. The absolute value of x times y is equal to the absolute value of x times the absolute value of y. The absolute value of 1 over x equals 1 over the absolute value of x if x does not equal 0. The absolute value of minus x is equal to the absolute value of x. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Now, this is called the triangle inequality. And last, the square root of x squared is equal to the absolute value of x. First thing we're going to do is we're going to convert the following function into a piecewise function. To do this, we do 2 steps, or at least I like to do 2 steps. I like to use this definition to update the function and then adjust the bounds appropriately. So the absolute value of x minus 1 over x plus 2 equals plus x minus 1 over x plus 2 if x minus 1 is greater than or equal to 0, and minus x minus 1 over x plus 2 if x minus 1 is less than 0. And now what I do is I simplify the expressions before the comma and make the expressions after the comma proper bounds with x by itself. So here, x minus 1 over x plus 2, a pretty simple simplification, with x greater than or equal to 1. And our second is going to be 1 minus x over x plus 2 with x less than. Here, take your time. See if you can figure out how I got this. See if you can do it on your own. And we're going to be exploring this in greater detail when we explore absolute value piecewise functions later in this prep course. So now what we're going to do is we're going to convert the absolute value of x squared minus 1 plus over x plus 2. And this takes a little bit more work. Absolute value of x squared minus 1 over x plus 2 equals, and now it's going to be x squared minus 1 if over x plus 1 if x squared minus 1 is greater than or equal to 0, and x squared negative x squared minus 1 over x plus 1 if x squared minus 1 is less than 0. Now, at this point, we have 2 things. We have to simplify the left side, and we have to deal with our equalities. And I'm going to deal with the equalities first. Okay? Now, I have 2 equalities. I want to figure out when x squared minus 1 is greater than 0. So x squared minus 1 is greater than or equal to 0. This gives me x minus 1, x plus 1 is greater than or equal to 0. My split points are x equaling minus 1 and 1. I draw my sign chart. I've got minus 1, 1, x minus 1, x plus 1. And now I'm going to complete the sign chart. Note that at minus 1 and at 1, I'm equal to 0. Positive, negative, negative, positive, positive, negative. I'm going to be positive, negative, positive. So my expression is greater than or equal to 0 when x is in minus infinity to minus 1 inclusive union with 1 to infinity. And likewise, it's going to be less than minus 1. So this is x squared minus 1 is greater than or equal to 0 when this is true. And x squared minus 1 is less than 0 when x is in minus 1 to 1, not including 1 and minus 1. So this allows me to update my function. X squared minus 1 over x plus 1 when x is less than or equal to -1 minus x squared minus 1 over x plus 1 when minus 1 is less than x, which is less than 1. And again, x squared minus 1 over x plus 1 is when x is greater than or equal to 1. Now here, we're going to simplify it even further. Because it's x squared minus 1, I get, we have plus 2, plus 2, plus 2, plus 2, plus 2. To simplify it even further, we're going to get x squared minus 1 over x plus 2 when x is less than or equal to 1 to minus 1. X squared minus 1 over x plus 2. This should be 1 minus x squared. 1 minus x squared if minus 1 is less than x, which is less than 1, and x squared minus 1 over x plus 2 if x is greater than or equal to 1. I highly encourage you to practice the following question, to break it up into its pieces. This breaking the function up into the pieces will be very, very useful skill to have, especially as we go on. Now that we've worked on breaking up the piecewise function into its parts, we're going to work with equalities involving an absolute value. Now, when we have equalities involving an absolute value, we're going to break the inequality into multiple problems using the absolute value function, specifying the restricted domain and using and. So we're going to split it up into multiple problems. Then when we've split it up into multiple problems, we're going to solve each subproblem using the split point technique. Remember to intersect the subproblems with the domain constraint. So this and we have to intersect. Once we have solved each subproblem, we're going to take the union of all valid intervals to give the overall solution to our equality. So here we have x plus 1 and x minus 1. And as an exercise, you were supposed to show that it breaks up into this function. So we're not going to go through that together, but we're going to have 3 separate equalities. Okay? We're going to have we have 3 equalities. We have minus 2x is less than 4. We're going to have 2 is less than 4. And we're going to have 2x is less than 4. But these, we have to reference the domains. So here, minus 2x is less than 4, and x is less than minus 1. 2 is less than 4, and minus 1 is less than or equal to x, which is less than 1. And finally, 2x is less than 4, and x is greater than 1. Well, let's look at our first example. 2x less than 4, and x is less than 1. Here, I have to solve the interval here and the interval here. Now, I will get 0 is less than 2x plus 4, or 0 is less than 2x plus 2. My split points is x equaling minus 2, drawing the sign chart, 2x plus 2, positive, 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 negative, 0, 0, positive, negative. And my overall line is going to be x greater than minus 2. But I also have the line x less than minus 1. So I'm going to intersect these two constraints. X greater than minus 2 and x less than minus 1. intersecting these two constraints is going to give us remember that this is at the point -1, going to give us open intervals from -2 to -1, or x is in -2 union with x going from -2 to -1 with open brackets. Now we have what happens with 2 less than 4 and -1 less than or equal to x less than 1. And here this is going to be greater than or equal to. Well, here 2 is less than 4. This is always true. So this here gives us the interval x is going from -infinity to infinity. And this bound is already solved. So if I take the intersection of these two lines, going from -infinity to infinity and -1 not including 1, and I intersect them, I'm going to get the interval -1 inclusive and not 1. So x is in including -1 up to and not including 1. And now finally, we're going to look at our third constraint. 2x less than 4 and x greater than or equal to 1. With 2x minus 4, we're going to use our split point technique. Again, you could solve this efficiently, but I'm always going to be doing the split point technique unless it's a given bound. So we get 2x minus 4 is less than 0, or 2x minus 2 is less than 0. Our split point is x equaling 2. Drawing our sign chart, we have 2 and x minus 2. Completing the sign chart, we have positive, positive, 0, positive, negative, positive, 0, negative. And I want to know when I'm less than. My inequality is less than, so it's going to not include 0 and be everything below. Which gives me the interval x being less than 2. Now I have to intersect these two intervals. So let's draw our two lines and take our two intervals. So I have less than, oh, this should be an open circle, less than 2 and greater than or equal to 1. Intersecting them gives me the points. I draw the points where each individual line changes, take the intersection, I include 1, I don't include 2, and this is going to be x is in 1, but not including 2. So now that I have my 3 individual constraints, I'm going to combine them using my union. So I have 3 constraints. I'm going to combine them using union. So 1, 2, 3. I'm going to draw each of these. So my first constraint, my second constraint, and my third constraint on these 3 separate lines. My first constraint is not at -2 up to and including -1. My second constraint is, or up to and not including -1. My second constraint is including -1 up to and not including 1. My third constraint is including 1 up to and not including 2. So at this point, I take the union of all 3 of these subproblems. So I'm going to draw dotted line down, dotted line down, dotted line down at all the points where it changes. And remember, the union is it exists in any of them. So it does not exist at -2 up to, it doesn't exist in -1. It does. And it still exists at 1 and up to 2, but not at 2. And it exists everywhere in between. So this is x going from -2, but not including, up to and not including 2, giving us our final interval. We can start to see our problems becoming quite involved.